sorry.
Special secret setups, including those that are based on intent. So now Matteo will go ahead with the tutorial.
Can you hear me?
Yes.
Also from Zoom? Oh, but maybe we have questions from Zoom. Yes, we have it. Yes, we will send the code. Probably this evening you will have the notebook with all the code inside. Okay. Okay. So we arrived here. So now we know how to set up, to initialize a quantum circuit and to execute it by collecting an outcome which is exact, so the final state on which you can compute probabilities and whatever you want. Or we can set the number of shots. So for real, we are executing like in real life. So we are taking one circuit and we execute it many times with the collapse of the Weiss function in the end. And so we collect the frequencies, indeed. What we are going to do now is to see a simple feature of Kibo that will be useful tomorrow, probably, which is the addition of more circuits together to build up a single circuit, which is very simple. And then we are trying to simulate some more realistic case, like some Bell state. You probably know what are the Bell states. But we start with this. So ideally, we want to have two circuits of the same dimension. With dimension, I mean the same number of qubits, same number of wires. And then we want to combine them together. Because many times you need to build circuits which are very complex, and they need to be constructed layer by layer in some sense. So we can start by initializing a circuit. We can call it C1. Like before, so circuit. And we can, for example, set 3 qubits. Then we add some random gate just to have something on the circuit. So add, for example, some gates dot Hadamard. We apply an Hadamard gate to the qubit 0, so we have superposition on 0. Then we can add gates dot C0. As usual, in the C0 you can set one qubit, which is the control qubit, 0, and one qubit, Q1, which is the target. For example, let's say like this, 1, 0, for example. Okay? I mean, doesn't matter. You can go. Oh, okay, maybe you can see better now. And for example, we can add a Pauli. So C1.add gates.z on the qubit 1, for example. Okay, this is one circuit. We can already print it if you like. So print C1.draw just to visualize the circuit. Okay? It's a random circuit. We are not going to build something with some specific meaning. Then we want a second circuit. So let's call it C2. Again, C2 is equal to circuit with the same number of qubits. And then we add some gates, like C2.add gates.Hadamard, again, for example, to the second qubit, which is the third qubit, because we start from 0. Then C2.add, let's say, again, a Z. So gates.z on the qubit 1. We can add some other gate, like a Pauli Y on the 1 again. And then we can add a control gate again. So C2.add. In this case, we can add a CZ, which is the controlled version of the Z gate, in which you use one qubit as control, and the second qubit is a target again. So, for example, let's use 2 as control and 1 as target. Okay? So we can print also the second circuit, C2.row. And now, okay, let's make some space maybe here, just to visualize them separated. Well, is yes. Okay. And then we can combine them together, and this is done by typing C1 plus C2. Everything is quite easy. And if you want to check it, we can Control G, Command G, take this, V, okay, and we can print C3. So as you can see here, the C3 is indeed the sequential application of the first circuit and then the second circuit. This is just a feature, but probably tomorrow will be very useful. Now, I would ask you, we are going to implement together one of the most famous quantum states, I would say, if we take into account a couple of qubits, which is one of the Bell states. So we are going to build the entanglement. We already saw this in the theoretical part of the lecture. So basically what we want is to take two qubits and to manipulate the state of the qubits in order to have one component of the state with half of the probability, which is in the 0-0 state, and the second half of the state in the 1-1. And this is very interesting and very important because then you are correlating the qubits in a quantum way. And if you are going to perform a measurement of one of the two qubits, and for example, we measure 0, we will know for free that also the other qubit will be in the 0 state. And this is one of the key points when you try to implement what we call it the quantum teleportation also. Okay? So you know for free one state after the measurement of the just one qubit. So these are just nice words, yeah? Up. Here? This is, you can do whatever you want. In the end, it's just, the important point is C1 plus C2 here, yes. Okay, so as we probably already know from the lecture, we need to create superposition in the qubit 0, which is the control qubit, and then we need to apply a controlled operation on the ancilla, on the second qubit, we can call it. We will know what is an ancilla probably today or tomorrow. And then we are going to see what happens, okay? So at first we need a circuit composed of two qubits. So we just type the same circuit with two qubits. Then we need to apply a gate to build superposition on the first qubit, which is the number 0 here. So we add the Hadamard gate. Let's see what happens on the fly. If you print the state, what you have is is a state in which you have the second qubit always in the 0. So we are not manipulating the second qubit, is still in the ground state. But the first qubit is half on the 0 and half on the 1. Now what we do is to add a controlled operation, which is controlled by the first qubit, the one in superposition. So C.add gates.C0, which is a controlled NOT operation. The qubit, the control qubit, has to be the 0. The target qubit has to be the 1. And if we now repeat the execution, you will see the second part of the state. The first part is the same. The second part of the state is now has become 1-1 because we acted on the target qubit only when the state of the control qubit has value 1. This is the key concept of the control operation. And it's quite easy, but in the end, just with a couple of gates, we built one of the belt state and a maximally entangled state. We can visualize it if you like. So we can collect some frequencies by executing the circuit, but with some number of shots, like we saw before, equal to, for example, 1,000 again. Then we collect from this outcome object the frequencies. And then we can visualize it. So visualize state. Frequencies. Opa. Yes, because we don't have the measurement gates. This is important. If you want to have the frequencies, you need to add the measurement gates, like Stefano explained it before. So we also need to say C.add gates.m and then we add the measurement to the 0 and to the 1. And visualized state is not defined. Fantastic. But it should be defined here, no? Ah, states with the S. Sorry, problems on the fly. S. Okay. Okay, as you can see, we have half of the state in the 0, 0 component and half of the state in the 1, 1 component, which is the same we saw directly from the state. So now we would like to ask you to do an exercise. I think you can do that when you like, and then we can think about it maybe tomorrow if you like. So just to take your time. And the exercise is very simple, and is to find the circuit thanks to which you can prepare the other Bell states here. So this is the same of before, but with the minus, before the minus 1, the 1, 1 component. Here you just need to build the 1, 1, 0 plus 0, 1 state, and here with the minus also. So it's just a matter of understanding which is the gate you need to add more to the circuit. Just to remind you that among the gates you have the Z gate, which is the flip gate, thanks to which you can flip the phase of the state. So take your time and do that, and then we can go on this the next time.
Just a comment about that. So when dealing with these different states, B2, B3, B4, try to think about the different gates, what they do, and then, because that will be the job. Now you have to understand which gates should you apply. Should I apply a Pauli X, a Pauli Z, when? Before, after applying the Hadamard and the control knot? I mean, try to think about it. Maybe you write down the expressions mathematically, and then you can use keyboard to control and check if the results are those that you are expecting. So you should see, if you Matteo go up to the analytical formulation, when you see these now, you have two positive numbers, the 0.70 plus 0.70 in the equation there. If you want to get the minus state, you should see the minus sign in front of the second term, and so on.
Yep.
So this is the difference.
Okay. So this is just a small exercise.
Any questions so far?
Okay. The next step is just to introduce you to some more complex but also useful gates if you, for example, like machine learning and you would like to build some model which is parametric, some circuit which is parametric. And we saw during the theoretical lecture that some gates are parametric inside. For example, the rotational gates, in which you can decide which is the angle of the rotation you want to implement, and then, for example, in a machine learning scenario, you can for example, want to tune it to understand which is the angle is performing some specific rotation that I need, okay? So for doing this, I would like to show you a specific architecture which I'm currently using when I do quantum machine learning, for example, in which we need to decide the number of qubits and the number of layers. Okay, so how many times we repeat some pattern in the circuit. So let's set the number of qubits, for example, to 2, and the number of layers, again, to 2. You can play with the numbers if you like, then it's not a problem. Then we built a circuit we call the circuit class, circuit with the number of qubits equal to n qubits. Okay? And then we want to add this pattern in a recursive way. So we need to loop over the number of layers. So for L in range and layers. Okay, sorry. What we do? Again, we want to add some rotational gates on the qubits of the system. So let me also loop over the qubits. For Q in range n qubits, again. Okay? And then we can add some gates. Let me add some rotations. So C dot add Ry, for example. So gates dot Ry. And here we need to specify the qubit on which we want to apply the rotation, which is Q, because we are looping over the qubits, and the rotational angle, theta. and let me set the theta to be 0 at the beginning. So we are basically not rotating the qubit. Then we add another rotation around another axis. In the block sphere notation, we are literally rotating the point around the axis of the block sphere. Gates.rz, so we just change the axis. Q equal to Q, and theta equal to 0 again. So for now, we added one rotation around Y and one rotation around Z for each qubit for a number of layers. To overcomplicate the model and to add some correlation between the qubits, we can add entanglement. Because the entanglement, and as you saw from the Bell state, is able to connect the states and the components of the state together. We can just doing that in a simple way, adding control operations, like C0, CZ, whatever you want. For example, we can say C.add gates.C0, and we use one qubit as control and the other qubit as target. And finally, we add to the circuit, we go out from the loops, and we add to the circuit the measurements. Yes? Oh, thanks. Here? No? Sorry, what you say? Let me, how to say? Control P. Now you can? Okay, sorry. Sorry, this is not my laptop.
That's okay.
It's fine. Okay. Fantastic. So now we can add the measurements. As you know, we can add measurements or to the 0 and to the 1 qubit, or to be more flexible, because we want to, to generalize this to a number of qubits which can vary. We can say range and n qubits. So we are adding measurement for each qubit of the system. Let me print the circuit also. C.draw. Okay. So as you can see, okay, let me go up. Okay. We are repeating the pattern, which is composed of Ry, Rz, control not. 2 times. If we increase the number of layers, of course, we have more layers. If we increase the number of qubits, we have more qubits. Easy. Okay, so this is a model which in principle can be customized by changing the values of the angles, so the parameters of the circuit. Let's see what happens. So now, what's going to happen if we execute this circuit on the initial state, which by default is the 0 state? The angles are zeros, so in principle, we are going to apply nothing to the initial state. So we expect to have again the computational 0 state in the end. Let's see if this is true. We collect the outcome object, which is equal to the execution of the circuits with a certain number of shots. And we collect the frequencies. So outcome dot frequencies. And now we can visualize the state. So visualize states. Frec. Okay, everything was, it's according how to say, what I was saying before. So basically, we didn't apply any modification to the state because the rotations were all equal to 0. Okay, so we are just applying nothing. And also the control not are not doing nothing because the control state is always 0. So we are not applying control nots. Yes? Yes? So now what we are going to do is to update into the, to inject into the circuit new angles and to see what happens to the final state. What we can do is to generate a new set of angles. So we need to know how many angles we need. We know them, but a nice way to do this is just to collect the number of parameters, which is equal to the length of a function, which is a method of circuit, which is c.getParameters. So let me do like this. Let me just save the parameters somewhere. So Command C. Here. In some vector of parameters, params. And then, yes, maybe this is smarter. We get the length of the vector. If you want to see this vector, we can already print it. So params. You will see we have only zeros for now because the angles we set in the circuit are all zeros. So what we can do now is to update these parameters, okay? So we generate a set of random numbers using NumPy. Let me do something which is quite a good thing when you use NumPy random number generator, which is to fix the random seed of the generator. So np.random.seed, and you can set it to whatever number you want. I would like to use 42. And angles now will be a set of random numbers generated using NumPy. So np.random, for example, from a Gaussian distribution centered in 0 with variance equal to 1. This is the random function of NumPy. You can select whatever random generator you want. I'm just generating new angles. How many numbers? N params. Let's have a look to these angles. Okay, these are just random numbers generated from a Gaussian. Now, what we do is to set these numbers into the circuit. So we say c.setParameters. And you just need to provide a function with a new parameters, in this case, angles. If we now try to print the parameters from the circuit, calling again the function c.getParameters, you will see that, of course, the angles are the same we were injecting before. So now the rotations, the Ry and Rz rotations, are customized randomly with these new angles we decided to set. We have a question from Zoom.
What's the order of the parameters here? The same you inject in the circuit?
Sorry?
The order of the parameters in the vector.
Yes, is in the same order of in which you added the gates. So in this case, we were looping, let's go up. We were looping over the layers and then over the qubits. So we are adding qubit 1, Ry, Rz, and the two parameters. Then qubit 2, Ry, Rz, and then you go to the second layer. It's the same order of the gates. Okay? I will answer to the question as soon as I finish here, from Zoom, I mean. And okay, we already visualized the parameters. Now we can execute and collect the final state and print the final state using the visualize states function. So again, we need the outcome object. Is equal to C with some n shots equal to 1000. Then the frequencies are the outcome dot frequencies. Frequencies. And then we can use visualize states of frequencies. And what you see is that now we have a different state. This is random because we decided to go randomly with the angles. But in principle, it's important to see that we are no more in the zero state, but we were able to manipulate it a bit. Of course, if you change the angles, for example, if you generate new numbers or if you change the seed, you will receive a randomly different state here. Okay? And the very final thing I want to mention, everything is fine from now? Questions? Okay. And the very last thing I want to mention is that typically, when you do quantum machine learning or you do any kind of application, you exploit the final state. And one way to extract information from the final state, of course, you need to reconstruct the state with the frequencies. You need to repeat the experiment many times. But then is to compute some expectation value of some observable, Hamiltonians, whatever, using the final state as in the bracket, okay? And what we are going to do now is exactly this. So we are going to set one Hamiltonian, one observable, and then to compute the expectation value of that Hamiltonian over the final state we get by executing this circuit here, which is randomly initialized with these angles. Then you should think about the fact that when you play with this kind of structures, then you can, for example, try to teach the circuit which is the best set of angles if you want to match some expectation value with some accuracy, for example. Okay, so for doing this, we can use something that is already implemented in Kibo, and we can exploit the Hamiltonians module and load one of the Hamiltonians which are pre-computed in Kibo. So H equal to Hamiltonians, and then we can select one of the Hamiltonians, for example, a transverse field Ising model Hamiltonian, and we set the number of qubits. Then you can also customize this Hamiltonian by setting the transverse field magnitude, the magnetic field thanks to which you can modify the Hamiltonian. But I mean, to the sake of this exercise, we just take the diagonal Hamiltonian like it is. So, okay, now we have loaded the Hamiltonian into H. And what we can do is to visualize some property of the Hamiltonian. For example, we can visualize the matrix form of the Hamiltonian. You can call it by typing H.matrix, and we can print it. These minus are because we decided to initialize the Paulis in some specific way in Kibo, but I mean, it's just a convention. In general, you see you have the eigenvalues on the diagonal, and then zeros on the off-diagonal terms. And then we can also extract some more information about the Hamiltonian, if you like. For example, we can print the eigenvalues, the eigenvectors, the ground state. Let's do that. H dot eigenvalues. Let me do some space also here. So -2, -2, 2, 2 in this case. On the diagonal, you can see them. Then we can print the eigenvectors. So you just call eigenvectors. And this is a matrix with eigenvectors on the columns. Or you can print the ground state of the Hamiltonian if you want. So you just call it ground state. You don't need it. Which in this case is the first column. I mean, it's ordered. It's 1, 0, 0, 0 is one of the two vectors related to the eigenvalue -2, of course.
I have a comment about this because if you remember, I was explaining that we have implemented Kibo-G, the just-in-time compilation. So when you select eigenvalues and eigenvectors, the code is already using multi-threading CPU, so the performance of this operation will be extremely fast. Okay, so it's not a single-thread algorithm; it's really using multi-core. And in fact, if you have a GPU available, all those operations will be done directly on the GPU. So you should expect extremely efficient results in terms of simulation. And this you get for free. I mean, you don't have to do anything. You just select the proper backend, and then all this computation is automatically done.
I can use all these three last functions to any matrix I define.
Yeah.
It would be a Hamiltonian specific.
Yeah, in principle, you can define any kind of Hamiltonian in Kibo. There are several ways. We are not going deeper inside these in this course. But if you mean if you can build any Hamiltonian, yes. You can also use symbols.
But I need to make it in the Hamiltonian framework, or I can use an array normally.
We have some Hamiltonians pre-computed in Kibo. If you want to have your very custom Hamiltonian, you need to build your own Hamiltonian on top of some class we have.
But I can define a matrix in NumPy.
Yes, yes, yes.
You can do that, and you can also use symbolic expressions. You can have a symbolic and then ask for the evaluation. And this is useful if you have large systems that you don't want to
But yeah, we have a class which is Hamiltonian with capital H, in which one of the arguments is form, and if you provide it with the or symbolical form or the matrix, then you will have your Kibo Hamiltonian with the same matrix form you wanted. Yes.
If you want to make class Hamiltonian using Austrian sum, you can do it.
Yep. Yep. And finally, what we want to do now.
Sorry.
Yes, sorry.
I have a question. This Hamiltonian you plotted in the energy basis, so it's diagonal already.
Yeah.
So how can I compare this with the computational basis or some different basis?
This is already in the computational basis.
So which because the transverse field model is not diagonal in the computational basis.
With the field activated, yes, you're right, of course.
Which field?
In case yes, I'm cheating here. This is not.
Okay, you just plot the magnetization.
I just plot the magnetic field equal to 0 in this case.
Okay.
But if you enable it, then it's not in the computational base.
We are going to see the matrix in the diagonal form,
Yep.
where we are going to have the eigenvalues and the eigenvectors in the computational basis.
Typically, yes. I mean, the eigenvector should be the same in the end. But if you activate the field, like here,
Okay.
H is the field, then you will see it's different, of course.
Oh, okay.
Now you have your TFIM Hamiltonian like you expected. And now if you perform measurements in the computational base, you will lose information because it's not diagonal there.
So this reading in the eigenstates of sigma z
Yep.
in the big spin sigma z.
Yes,
Yeah, okay.
yes. But let me just come back to the simple case. Of course, this is true. Thanks for the question, by the way.
In the safari of IC models, you can have like x-axis interactions.
Yes,
interaction
yes.
with the field, so
No, it's perfectly right.
it's
Yeah, you're
very
perfectly
good
right.
to specify.
Yeah, thanks. And okay, finally, if you have your Hamiltonian, also if you have it not diagonal, what you can do if you want your exact expectation value over some state, then you can call a simple method of the Hamiltonian, which is h dot expectation. And what you need to provide to expectation is a Kibo state. So in our case, let me just collect the state associated to the circuit with the rotations I was defining before. So state is equal to C. We don't need the number of shots in the end because we are doing exact simulation. You can also put it if you like, but in the end, what we need here is just the outcome, the part of the outcome, which is the state, so C dot state. And then we just pass as argument state to the expectation. And what you get is the expectation value, the exact value of the expectation value of this transverse field Ising model without the field, but if you want to activate the field, you can also do that, over the state you get if you execute that circuit with that rotations. If you change the rotations, you change the circuit, and so you change this expectation value. How is the situation so far? Okay, good.
When we have a ground state which is degenerate, it gives a random ground state or all the...
Sorry, can you repeat?
When you have a Hamiltonian, which the ground state is degenerate, you have
Yeah.
many...
You have the first column.
Oh, the first one.
Yeah, we just order them and we pick the first one in the list.
But you don't give all of them.
No, no. We just use the first one in the list. Yeah.
This state that we get, we're just can't we see or we
The expectation?
yeah, but can we get the state like density operator?
Yes. We will see it if we manage to, if we have time, hopefully in the last lecture, we will see the noise. And if you go through the noise picture, you will need to pass from the cat notation to the density matrix notation. And you can do the same, yes. For now, it's working with the full state vector, the vector, indeed. But we also support the density matrix, and you just need to initialize the circuit with density matrix equal to true. And the final state will be the density matrix instead of the state. So I think for today we are done because we are also exceeding the time. So, yeah.
Okay, any other questions?
Yes, there is a question from Zoom.
I have one question.
Can't hear me? Can you hear me from Zoom? Can you hear me from Zoom? Wait, okay, you can hear me. So yes, just giving the time to answer to the question on Zoom. They are asking 3 questions. First, what is the difference between the Kibo and other such Qiskit, Penny-Lane, Circa, and etc.? You want to answer?
Yes,
okay. Okay, maybe I will answer to this question, and then I will let Stefano to answer to your question. Yes. Yes.
My question is about my colleague's question, because he said that we can import some arrays in a matrix form from NumPy or something to execute there in your playbook.
Yes.
Is it efficient? It's okay to do it, or it's some kind of tricky thing? It's okay
If you stay in the NumPy picture, then you should. I mean, you are doing the same we are doing now. We are working with NumPy, Numba, stuff like this. If you work with like tensors from TensorFlow, then it should be. I mean, it's a bit different because you need to switch to the TensorFlow backend, and then we need to do some modification. You will be slower. But if you use NumPy, no, you can do whatever you want. Yeah.
Keep in mind that it's true. And then there is another thing. If you're planning to simulate large states, I mean, remember that if you build a matrix, then you have a 2 to the n times 2 to the n. No? Ideally, you could write just the symbolic expression of the Hamiltonian, and then use the Trotter theorem to have a distributed representation, and this will be easy to simulate. So usually, if you are planning to do that, just go for the symbolic, and then you trotterize and execute the simulation with after trotterization. No? So this is the best you can do, no, with this.
The question.
Just a question from Zoom concerning why Kibo versus the other libraries. I mean, frankly, when we started the project was in 2020, and we tried to investigate the status of Qiskit, Circ, and all these frameworks. The problem is that we had labs and we had to operate laboratories. If you check their codes, you see that they provide the upper level, so the language API and the simulation, but they don't go too deep into the drivers. So you cannot control, you cannot talk to an FPGA, to open firmware, to even a commercial product. So this part of their code is closed. And that's why we decided to go for Kibo. And furthermore, when doing benchmarks, we saw the difference in performance, and that was really something important to improve. No?
Second question is if it's possible to use it combined with other platforms. And maybe I could answer here, saying that we support the OpenQASM language, which is a sort of assembly in the quantum computing. And so I think, yes, through the OpenQASM translation, you can do that. But also now we have the Kibo Cloud backends, which is just an extra application, an extra package, in which you basically can write your circuit in Kibo and you can run on the other platforms, or also in the cluster of IBM, the AWS, and so on. Wait. Okay, let me go down here. And the third question was about the multi-controlled gates. The standard way to do that is to use, as you mentioned, you select the 1 qubit gate and then you set dot controlled by. This is the best way to do that, yes. There was a question here, yes?
When we are working on real hardware and want to simulate precision value of some observable, we have to run circuit many times in making many measurements in different phases. In this case, it doesn't do something like that. It doesn't make a sample of circuit and measurements. It just calculates the product factor between A, C, and C.
In the exact simulation, yes. In the simulation with the frequencies we saw, when you set the number of shots, then you are sampling the final state. So yes, in that case, you are simulating what happens for real. So you are also, if you go even further and you set collapse equal to true in the measurement gate, there is an extra argument in the measurements. You can set collapse equal to true, and then you will get a list of collapsed states in the end. So that will be what actually happens in the lab. Depends on what you want to do. If you don't want to do don't want to go to shot noise simulation, so with exact simulation, then yes, you are doing matrix multiplication. If you activate the measurements, then no, you are doing actually what happens in the lab. And other question from here. Can we run Kibo code in Rigetti on other quantum hardwares? Rigetti not now, but other quantum hardwares yes, because we are writing the Kibo cloud backend. So yes, maybe I already answered to this. Do we have access to this notebook? Soon. We are going to update the notebook in the repository with the one with the code. Yes.
Yeah. So so the question is, how can we tweak the Kibo backends to execute it on cloud providers or in Kubernetes and all the. So the point is, if you're planning to simulate, for example, if you wanted to rent an Amazon AWS instance, you can do that, and then you install Kibo and KiboJIT, and KiboJIT will just compile on that architecture. And you can tweak the number of threads. If you remember here when we started the tutorial today, we had these options to here. For example, the get thread, so you can convert this get thread into set threads, and here you can select your desired number of threads. And this setup is feasible everywhere, in any place where you have a server. Okay. And also the acceleration. So if you rent an instance with GPUs, then you can just change the KiboJIT call, the platform from Numba to KuPy, for example, here. And then this will automatically use the GPU. Okay. Now, there are many backends. So if you are doing machine learning, classical machine learning that is controlling quantum circuits, you might prefer to use the TensorFlow backend, because then they can create a united graph with all operations and do gradient descent. Same for PyTorch. So it's up to you to decide what is the best setup and where you are placing to deploy. No? For simulation. If you're talking about hardware execution, then we have a wrapper. So in the plot we have a backends for IBM, and this is the QRCTII, which is our backend for labs in our network, so in Italy, in UAE, in Asia. Those will be available soon, and I mean, they are not a company, so we are not, this is just a research institutions. So at some point there will be a web page where people can register, and we can provide some quota to execute the jobs. Okay, and we are also working in one instance for brackets, AWS brackets translator. So that's what we provide. Now, if you are in a lab, in a research institution, then you go down and you use Kibo Lab directly. So Kibo Lab will talk to your instruments in the lab, and you send the circuits directly to the instruments. Okay.
Any further question? If not, we are free to go.